Welcome to Homework Lib.
Okay, so this is a problem investigating different energies and energy densities associated with a toroid. That's the donut-shaped type of solenoid. So there's a lot of numbers. Let's go ahead and start assigning variables to each of these and then converting them into SI units in order to make our lives easier down the line. So that's the cross-sectional area. And the current is a whopping 5 amperes. And so there's 5 relatively short parts, but to start off with part A, we want to know what the magnetic field induced is. So that's given by mu naught n I. So we don't know the number of coils per length, but we can solve for that by dividing number of coils divided by circumference. And then let's plug in numbers over here to save some space because there's going to be a lot of parts in this problem. So we'll plug in mu naught, plug in number of coils, plug in currents, divided by 2 pi toroidal radius in order to get a magnetic field of 2.5 times 10 to the minus 3 Tesla, or 2.50 millitesla. Good. Moving forward, in part B, we want to know what the self-inductance of this solenoid is. So we can do that by using this formula. We don't know the magnetic flux, but we do know the magnetic field strength and the area. So we can plug in numbers to solve for that. Recycle our answer from the previous parts. Divide by current in order to get the self-inductance of 6.00 times 10 to the minus 5th henries. Good. Part C is asking us for the total energy stored in the magnetic field. So we can use this equation to solve for that. Recycle our answer from the previous parts. Plug in current, that's over here, squared, don't forget the square. And see that there's a very tiny amount of energy stored in the magnetic field, much less than a joule. And part B, find what the energy density is. That's supposed to be a lowercase u as opposed to uppercase u, so a slightly different formula, or rather a very different formula, in order to find out what that is. And then our magnetic field strength, which we solved for in part A, squared, gives us a magnetic field energy density of 2.49 joules per cubic meter. And in part E, we want to verify our answer in part D by taking the actual energy and dividing it by the volume. So that's lowercase u on the left, uppercase u on the right. And then we can solve for the volume by multiplying the circumference by the cross-sectional area. And hopefully it gives us the same thing. And when you plug the numbers, it does turn out to give you the same thing, which is good. And we're done.